Hello. So I guess we are only two of us here today. We'll be this time. What we had was periodogram and the frequency domain characterization. So it's more of hands now. So now you'll be able to see that how well we can see and interpret the data. What are the different kinds of measures through which you can use the data, and then what sort of things that people started proposing and to where which extent today we are in there. So Ayush and Meg, have you seen the slides, or sorry, have you seen have you went through the lecture slides or the lectures that are there for week 7? Okay, so I
Yes,
see
ma'am.
okay. So do you have any doubts, specific doubts, or would you like to me to summarize as we do usually?
Ma'am, I have one doubt.
Yeah, go ahead.
Ma'am, in the window function, when we
Yeah.
take the Fourier transform,
Hmm.
so, ma'am, my doubt is that the limit is minus pi to pi or minus 1 by 2 plus 1 by 2.
Okay, so actually it depends on you or whatever. So whatever there is in the definition will stay as in the definition. But whenever you are applying to an actual signal, so there you need to see that from where to where the signal is actually lying. You have the signal there, so you'll consider the limits accordingly. But if it's in the definition, if it's negative 1/2 to 1/2, it will be negative 1/2 to 1/2. Probably what I saw was negative 1/2 to 1/2. Pi would be when you're considering radial cases, or you have your functions in it's like angular frequencies considered. So see the if it's dt or if it's d omega there. Accordingly it will vary.
Ma'am, because, ma'am, in assignment, there was a question.
Hmm.
So, in that question, it was mentioned that to obtain a smooth spectrogram, the periodogram S of omega is convolved with a filter W of omega in frequency domain.
Hmm.
Condition that should be satisfied by W of omega.
Hmm.
And
Hmm.
when sir was actually teaching in the lecture, then there everywhere there was a limit minus 1 by 2 plus 1 by 2. And an
Yeah.
option, no such option was given. Limits were given minus pi to pi. W of omega should be greater than equal to 0 in minus pi to pi, 0 to pi, minus pi to 0.
Mm-hmm. So there, do you remember if Sir has used omega in between the frequency filters, or what has he used actually? Even I don't remember it that accurately, but let's see. I've also used the same snapshots today. So
I mean, the previous slide.
this one for the base, no, right?
Oh,
This
ma'am.
one.
Yes, ma'am. Ma'am, you see, ma'am, in integration, the
Mm.
limit is taken minus 1 by 2, 2 plus 1 by 2.
Mm-hmm. So here, then it's just the basic convolution of the signal. So here it's just the Fourier transform. When it's multiplied, we get the convolution. That's it. What he was trying to say from this point. So what the question here was. Wait, let me share my screen. So the question, this one here, to obtain a smooth spectrum when this is convolved with this in the frequency domain, which of the following conditions should be satisfied? So you see over here that the limit here is omega, so it's dealing in the angular frequency. Now we know that the weight should be positive because we want a positive, like we don't want negative functions in there because the autocorrelation function and all those limitations. So then you need to see that what particular limits you'll keep on omega so that you get it positive. That's it.
So, ma'am, limit will be minus pi to pi only.
That you need to be sure. It's like if it's a b, have a look. It just
Actually,
basic.
I was thinking that,
Hmm?
ma'am, it was sure that W of omega should be greater than equal to 0. This I
Hmm.
was confirmed in this point. But, ma'am, actually, I was confused because of the option none of the above. I was thinking that maybe they have played a twist game.
if it's negative 1 by 2 to negative 1 by 2. No, because that was just in cases like
Yes, ma'am.
it's just a normal case or a scenario. It would be in the textbook or where people have taken, okay, negative half to negative half. So it's just given if considering the period is 1. If the period is 1, then saying it's either it can be negative half to half, or it can be 0 to 2, 1 by 2. It can be like that. So it depends there. Also here it's just a basic convolution and we are dealing it f. So it's the function that is shifted is like in the frequency domain. Here the function which is shifted, it's in omega, so we have a factor of 2 pi f there. So that's why I probably gave out most of the answer. You just have to mix all the points and you'll get the answer then. Okay, I guess others were mostly fine. The main lobe ones and these ones. Okay, so no further doubts then. Sorry for this noise. There's match going on here. If there are no further doubts, then we'll go ahead with the lecture slides. If you do have any doubts, let me know. Then after that, we can start the session. Anyone has any doubts? Okay, so I guess not. So we'll start. So the slides are visible, right?
Yes, ma'am.
Okay. So frequency domain characterization. Now all of the references that you like we had previously plus one, this is the newer reference by Stephen MK. So here most of the definitions, formulas that have been there in the lecture slides would be there in this book. You'll also get a more precise and like brief description. I use some of the text from there to understand because it was getting confused for me to understand from the lecture slide, so I normally use a book. So you can just go through the book if you have any further doubts, or you can see. I don't think so there are more numericals in it. It's more of theoretical based and just to give you an idea of that. It's like the concept. So you can have an idea. It's like you can just Google or cross it out that which particular authors have again referred this book, so that there would be more questions, so that it would help you gain a more practical understanding of it. So what's it's like till now we were looking into time domain characterization. We looked at all sort of processing techniques. It's like from regression to correlation. Then we also saw peak detection, thresholding, everything we saw in there. We saw different kind of filters. We saw the modulation, all those things we saw. Now what we have to do is like now we are shifting our goals and our it's like objectives to frequency domain characterization. Now why frequency domain characterization is like it's more faster. If we are in time domain, the more problem is the noise. Everything's not that cleaner, and if you do averaging, usually it won't help. So you need to come up with more amount of techniques. For example, heart rate is easy to express as 72 beats per minute, but one won't say that it's in respect to cycles, like 1 by minute. So if it's in this amount of cycles, so it's easier to express in minutes, that's in time domain, but rather to express or let it term in a frequency domain. So then what do we do usually is like we isolate signals, we take certain windows, and then we it's like do our processing on it. Simply similarly that we did in a continuous signal divided into quasi stationary signal, and then we did it. So then it was just confined in time domain, so we had more number of problems, so we had to go through the problems, read into the issues, and then solve it. One such kind of a case study was that for this dichrotic notch, where we had different kinds of noises, say for S1 and S2, which occurs when the valves close and or it's like the valves open and close. Now what we saw in there was after a systolic pressure arises, there's a it's like slight down pressure that we see is called as this dichrotic notch. So people weren't able to visualize this dichrotic notch. They weren't able to actually see that where is this occurring, what is the time domain, what's the timestamp respect to it. So then when converting all the issue into frequency domain, doing some similar processing, very easy methods, we were able to see, and then we converted it to back. So we'll start. So first of it is the periodogram. Now if you see what is this periodogram is like, combining these two terms, we have a period and then a gram. Gram is usually for the visualization, and period is like about the time stamp or the time duration of our entire window. So, okay, wait, I guess there's a bracket here. Okay. So we have this periodogram now. Here people is like, how do we give it as? Like it's represented now. This is your signal where x of n is a random variable. We have represented it as entirely the function of the signal with its real and imaginary parts, summing it up into the duration of the window that we have by total number of points, taking expectation of it since it's a power spectral density or a periodogram. Now here, what exactly that we are doing is like this. If you see and visualize, we normally use write the definition of Fourier transform is similarly like this, and then we average it eventually. So this is the random variable, as I said, and then we are taking limit as till infinity, so the infinite extreme case. Then if it's a power spectral density, we can also write this periodogram as the power spectral is like can also estimate it in the similar ways. So if you see over here, it can also be expressed as the autocorrelation function. And if you see, it's like if you or if you don't see a relation in between them, we see that okay, autocorrelation function is nothing but the correlation of the signal with the signal itself in order to see that where's the maximum energy or how the signals are aligned well, how much the distribution is, how the spread is, everything like that. So we see that if we have this autocorrelation function, what we have to do is like this won't be nothing but the conjugate, two conjugates like x of n and x conjugate of n multiplying with each other. So what do we see over here is like if we have x of n exponential of this part, if we split it up, now keeping in mind that if we just split it up, it won't be actually x of m times conjugate of x of m, because now the lags would be different. So we need to keep it in mind that okay, the lags are different because the two series, the two timestamps, everything's different. So we it's like instead of taking the same variable, we change it and we add one more summation term over here. However, the number of average total number of points would remain the same because it's the same series eventually, but we are taking the correlation between them. So the number of points, which is like how we are denoting it, where at which instant of time we are correlating, it would vary. So then this correlation would be determined as m minus m. So because of these two variables, but then there's an assumption, it's like inherent assumption there that if we have a term as g of m minus m, we take the total number of points as 2m plus 1. It's like normally what we had in the same sequence minus k. Now k here is a factor which will determine how well you are able to smooth it in. Now if you see over here, this is our original term. Now taking the total number of terms inside, now it's like substituting this by a weighing factor over there, and then it's like k, you determine it there. So we have 2m plus 1 by k. Now then if you see here, this particular part 2m plus 1 and this, okay, the same equation is there here. So if you take it inside, this would be 1 minus mod k by this. So you have this equation. You can again represent it as like the autocorrelation function times of this particular variable. But now here it is a function of k, hence we change the limits, and then this limiting case is no longer its hold, because if you add it in here, it would be, it's like if it tends to 0, sorry, to infinity, this term would be eventually 0, so this would be 1 and this times. So then we don't have a dependency of m, and this terms would be dependent on k itself. So we change the terms from negative infinity to negative infinity to take the entire window. So by definition, we had this. Now, if you say that, okay, if it's limited and if it's positive, so if our x of n has terms from 0 to n minus 1, so our estimated periodogram would be like this. So it would be x of n times of our function. Since it's a power spectral density, we have a square of it. Yes, we also did square initially. So it is normally defined as this. And then averaging in the end is like taking the total number of points. So what's the interpretation of this periodogram estimator at a given frequency? Now, what you are interested in to not finding that, okay, how the function or the spectra is giving you all the points at the entire spread or over the entire duration, but not at a given frequency point. So power spectral density will give you the energy at a particular frequency. But when limiting and taking the expectation, it is nothing but the power spectral density, but it's not possible to implement it practically. So what we do is like we take, it's like here if you see, this might be similar to how we do convolution. So it's nothing but the energy at each and every instant of time is like the function itself lag the signal by a particular point, take the Fourier transform of it as well as square the magnitude, so you get the power spectral density. Here they have defined this particular function as the impulse function that can be given as this normal impulses are represented, that's it, not more difference. So this is the impulse response of a LISF filter. When given an impulse to it, the response that we get is an impulse response. So you represent the impulse response by this. Taking the Fourier transform of it, we get this particular function. So now if you are not aware that how to compute the Fourier transform, you might want to go backside. So basically the fundamental is very similar. It's like you take the function however the shape of the function be it, you differentiate the function once, you differentiate the function again, then you see something. Now write the function in terms of like you differentiate it till you get impulses. Now it was simple here because you got the impulses, you have exponential, since you got, hence you got a sinc function here, something like sinc function. Now you have everything in impulses. Now you write the impulses and then take the Fourier transform. So having impulses, and then you have the time domain conversion, the properties, frequency domain properties, then it's very much easier to write a Fourier transform. So you might get any such functions or shapes, like to say if what's the Fourier transform of a rectangular function, of a triangular function. So all sort of things will come. So for that you need to be, it's like very quick in determining the Fourier transform, because there's no such short trick for determining Fourier transform as such. Okay, back to the point. So here our h of n is, it will behave as a band pass filter over here that is centered at this frequency of f naught. So our periodogram estimates the power at this f naught, that's the center frequency, when we filter the data with a bandpass filter that is by this h of f. Hence we sample the output using this sinc function or a sampling function, and then compute the magnitude square of it. So in a way we get this as like power spectral density. That's it. So then here you see that there's another variable. This was usually you took it as the total number of points. So then n is a factor here necessary to account for the bandwidth of the filter. So if you take a 3 dB bandwidth of a filter, it is proportional to 1 by n. Now, do you know, or are you aware of how do we compute? It's like if we have a particular function, say a Gaussian function. Now Gaussian is something like this. If I have to draw it here. Normally Gaussian is something like this, right? So and then what we do is like normally we whenever we represent a function, okay, just neglect this spike in here. So we normalize all the functions that we have. So we normalize it in a way. Now the peak is 0, and what we get over here is like the negative estimates of them. Say if this is negative 3 dB, this is negative 6 dB. So in signal processing, the frequency response or the bandwidth of the filter, we give it at different kinds of ways. So there's full width half maxima, half width full maxima. So it's not, so here if they are taking a 3 dB bandwidth, it's, they are saying that okay, it's proportional to 1 by n. It's like this. That's it. So just if you have an idea of about this context, that's it. Okay. So there are some properties to take into mind. So if we have more number of data, then the periodogram essentially is a power spectral density, because in power spectral density, we are considering the entire spectra, entire duration of it. However, periodogram usually deals with the estimated power spectral density. That is nothing but within a certain window or the function. So it's like the estimated function, it after a certain point, if we have more number of data, it converges to the power spectral density. So this is consistent estimator of the power spectral density, but it's not an actual estimator of it. So then what's this consistent estimator? It means that the estimator means that is of this R periodogram is equal to the true PSD's mean as this n, the number of points tend to infinity. But then at that case, the bias would be 0, hence the variance would be 0, because now you're considering everything in your data set. You are not, it's like you're not reliable, or you aren't actually specific to this particular window. You aren't focusing on that window. So what you'll be doing is like taking everything. So if even if you have something positive and negative, it would essentially will cancel out. What you'll get is the actual true nature of your data, but not only the local value of your data. That's it. So there are some properties into it. So one such is called as okay, so if we have say a variable theta, and this is the estimated value of this theta, so there are two properties called as bias and variance. So this is how we define bias. That's nothing but expectation of the estimated value of theta negative of this our variable theta. And how do we give variance? Variance is nothing but the spread of the estimated result from the true value. So you know what variance is, standard deviation ka square. So we just took the estimated function of this expected function of the standard deviation, square it up, so we get a variance. So the periodogram can be shown identical to the Fourier transform of an estimated autocorrelation sequence. So initially we had this particular part, but this was our biased autocorrelation estimate. So you can't actually say it as, okay, this is the autocorrelation function. It's the estimate of our own this particular function. So the estimated PSD, that's the periodogram that we have. So how do they again represent this estimated biased autocorrelation curve estimate? So this, like, average it up, you have these two functions at two different instants of time. Now since it's dependent on k, so we'll actually have a term over here, so n minus 1 minus m mod k, because we add it in there. So now we need to compensate it somehow, so that is negative k. Here if you see, the limits were like k equals to negative of, it's like we're symmetric. Here it won't be, because autocorrelation function, it needs to be in positive, so we took it in the same way. So let's see for bias. Now what bias is? Bias is the first order moment. Essentially it's the first order moment, and variance is a second order moment. So how do we represent bias? Is like the first expectation of our estimated periodogram. So how do we do is like take the expectation of everything. Now you took an expectation of everything, so you got this term over here. It's like n minus mod k, because now you're not, it's like here if you see the points were from negative, it's like were symmetric. Here it was from 0 to this particular point. Here now you change the limits for k and n. If you notice, the points are like this. Now if you see, k's limits were same, but you no longer have the small n term over here. So negative, now this is symmetric. So in order to, it's like compensate for that extra terms in the negative domain, you take n minus mod k divided by the average like total number of terms that you had. So if you see a relation over here, somehow you see that this expectation of this periodogram is nothing but the Fourier transform of these two terms. So if you say that, okay, this is somehow a weighting function and this is your autocorrelation function. So multiplication in a time domain is nothing but convolution in the frequency domain. So we have this particular convolution of our own estimated periodogram with respect to that of our weighted window. Now they are saying that this weighted window is nothing but the Fourier transform of a rectangular or a Bartlett window. So this is something new over here. So what is a rectangle? Sorry, a triangular or a Bartlett window? So the same thing. If you don't know how to take Fourier transform as of now, you can go see. There are different kinds of tutorials on YouTube. One says that I feel is more of easy to go through is for about Nezo Academy's videos. So it's more of easy to go through, and he solves more of problems. So it's nice, and you can have a look at there if you haven't yet. So this Bartlett function is defined as this. So within this particular intervals, it has some value. After that, greater intervals, it doesn't have a value. So then again, it's mod k, so this function is symmetrical around two axes. So even if you estimate for one side, like from 0 to n, you can just take the same values for a negative n to 0. So they have given its Fourier transform by this. So it's essentially a sinc function or a sampling function. So if you have no, it's like for a triangular function, for a rectangular function, it's like Fourier transform is essentially the sinc or the sampling function. But if you go into, say, there are some windows like Hamming window or Hanning window. These all windows are essentially defined by the impulse response of the function. So there's no way to generalize it in this with respect to sine or cos function. Let it be into the simpler functions. It's like this only. This means here that the periodogram was nothing but the convolution with this Bartlett window as well as our power spectral density function, yielding a smooth version of the true PSD. And hence this is over here is biased for a finite data set. But if you take it for, it's like for any tends to infinity, it would be unbiased. So we won't be able to see where the trend is actually lying, because here if it's n tends to infinity, what they are talking about is from 0 to infinity, but not from negative infinity to 0. So given a particular window, you know that, okay, it would be symmetric because your function is like that. Now you don't know how the function would behave if it's like greater or lesser than negative n. So that's a fundamental logic over there. Then similarly for variance, if you see, it's a second order moment of the periodogram, so take expectation everywhere wherever you see. So then you have here 4 variables over here. So similarly 4 summations, but then the fourth order moment would be kind of difficult to evaluate, and there you might need to do some numerical methods for the same. So what do we do is, like, we consider some of them is a white noise. It's like x of n consists of a white noise, and hence it can be represented as a sum of all those fourth order moments. Now you know that okay, it's a fourth order moment, it's a variance taking the standard deviation. Now since we considered that okay, it's a fourth order moment, we have sigma square times sigma square, we have sigma power 4 over here, and then representing all in terms of similar impulse functions. So like having a response only at that particular instant of time. So if this particular value is equals to this, if this value is equals to this, or if these both are equal, these both are equal, then only our function exists, else we don't have anything over there. So now if you see over here that this way expectation and this variance is sigma power 4, so a lot bigger term. Okay, we'll get to it then. So then expectation, they said that okay, it's sigma power 4, and then we like solve these terms, and then we again got some functions of sine over here. It's essentially the sinc functions. Again wrote the covariance. What covariance is, like the expectation of the two periodograms or the power spectral density minus of individuals of them. So we got the terms. So what we saw is, like, either you take the expectation of a periodogram or the variance of this power spectral density, what you get is sigma x square over here only. So that what we saw over here is again independent of this capital N, the number of terms that we had. And again, it's an unreliable estimator because the standard deviation is as big as that of the expectation or the mean of the signal that we had. So where did this mean went? Mean, I guess. Okay. So from here only, if you see, it's inversely proportional to this, and for bias, I guess it was here only till this point. So here they are trying to say that if it's in term of sigma power 4, it's very big, and then if the variance increases, the data is very fluctuating. So you no longer have a true value or a ground truth about your data. So it's very big, and if the average and variance are overlapping with each other, so it shouldn't be the case. Variance should be lesser, even if you take two more and more amounts of sets or trials on your data. So then they saw that okay, if they took different kinds of frequencies, say some harmonic frequencies. So I hope you know what harmonic frequencies is. Like if you have a signal that has a fundamental at f naught, there are different harmonics associated with it. First say is like a subharmonic, or there's a I forgot the name, but there are multiple intervals. It's like multiple integer values of the frequencies that we have. One such of half of the fundamental frequencies is like, or 3/2 of the frequencies. I actually forgot the name. Subharmonic is one such that is half of it. Ultra harmonic is like one plus the integer function of it. So there are other kinds of harmonics in there. So if you say you have two different kinds of frequencies, say some integer m by the total duration, another integer m n by the total integer, where these are two distinct one in this particular frequency range. If it's for even, if it's this, if it's for odd, it would be like this. It would essentially result in zero covariance, and the values of this are uncorrelated. Since they are uncorrelated, we know that at different frequency points we don't have the data that's related to each other because it's independent of this point that's in. So essentially we'll have everything as zero. So these features lead to rapidly fluctuating periodogram that's recorded as the record length will increase. So as it, same thing again and again, that as the estimates go towards is like as n approaches to infinity, it's very unbiased and you can't actually give the essential true value of the data. So in some applications, sinusoids or narrowband signals are embedded in the white noise is of importance, and their data windowing, that x of n, is important to reduce the side lobe frequency. So I hope you that you know what side lobe over here is. That it's like, just I'll give an idea that if you have something like this is the main lobe of your signal. If you have seen sinc function, so something like this that you have till the signal becomes zero. So this is called as the side lobes of the signal. So actual trick point in here is like, if you see the level of the side lobes, it will determine the contrast in your signal, but if you see the level of the main lobe, it determines the resolution in your signal. So these are the two fundamental properties that you can again capture from the side lobes, okay, or from the main lobe. So then what to do is like, if the periodogram is not a reliable estimate, what do we do? Because here the variance was very big. We had fluctuating data. It was as same as that of the mean. Again, the values weren't correlated to each other. So then should we take an average periodogram? Okay, let's do that. So people were trying to see that, okay, averaging would perhaps will help, because in time domain, what we do is like we take average again and again. We take moving average, we take a windowing average, we take either if it's a non-stationary signal, make it stationary, then we do the averaging. So it was very common at back then. So what we do is like we assume that there are k independent data recorded in there. So we had it's like finite length sense of data, and the periodogram is estimated divided as we have. So the average would be the estimates of each and individual function, as like of each and individual state. So then if you have want to see the individual state of periodogram, it would be represented as we saw initially. So the mean value of the average periodogram is same as that of the periodogram with any data set. Now here they think, oh, it's like they kept in mind, or the inherent assumption was that each and every point at any particular instant is not varying, and it's like how they are doing the averaging is like consider overlapping every point to each other point. It's like if it's t equals to t1, the spectra would also be at t equals to t1. So the mean value what they saw is that is of the average periodogram was same as that of the mean value with any data set with any given points. Again, for the variance also, say they saw a similar function is like a relation was there, but there in that relation they saw that it was inversely proportional to k, so now it was degrading. Okay, that's a good point, that our variance is now decreasing, because essentially there the variance was as big as mean, so now it's decreasing somehow. So we have a common approach over here where we take n as kl, but then there are different kinds of techniques to be done. Is like one such as window close or window data technique, where you have some estimates, and within those estimates you find what optimum value would be. But then after some point of time, people saw that, okay, if you just tune it, it's like manually vary this number of points from say one any given points, because essentially these are nothing but the scaling factors. So you change the scaling factor in a way to obtain a smoother function, a positive estimates. If the variance is less, the data is not fluctuating so much, then you can get, it's like you just tune it or optimized it manually, and there only you can get those values. So was not different. So this was all about the periodograms and how people went from normal periodogram estimations to the average periodogram estimators. After that, one such technique was for Blackman-Tukey spectral estimator. So what was the major idea over here? So people, it's like this two people, Blackman and Tukey, they saw that, okay, the periodogram was a poor estimator for PSD, so they should do something else about that. So what next they tried doing is like, now they explained using the similar formula that we had initially, where the autocorrelation function is also the same, taking the even and symmetric window over here of the autocorrelation function. So now they saw that, okay, because of this autocorrelation function, it's performing very poorly. So instead of taking this initial terms and the positive terms, it's like take it's like focusing on the all terms or the symmetric terms, they were now focusing on the last lag of the signal, that's on only on the n minus 1 part. So they took the autocorrelation function as like two conjugates divided by the entire spectrum. But now here they saw that, okay, it was not averaged for all number of points, so the data had more number of variability there, and it was biased no matter how long the n to be, because we had only a single n minus 1 over here. So what to do next? We should either increase the number of points, or we should take the mean of it. So what they did is like they just went and took the average of it, took the expectation of that particular term, and then wrote it as like over here. But then this estimator was an unbiased one, because we can now use this unbiased autocorrelation function by replacing this particular point n by n minus k, what we had in there, because we now need to match the limits with respect to the total number of terms where we are doing our calculation into. So now, okay, something's decreasing, values are limiting, at limiting cases they are trying to exist over there. But they saw that, okay, due to this it may lead to negative spectral estimate, as the unbiased estimator does not guarantee a positive semi-definite sequence, because till now what we had was everything was positive, the terms were positive, correlation sequence was positive. So what can be an alternative approach? Increase the number of points. It was due to the poorer estimate because higher lags were there due to a fewer number of lag products for this averaging. So can increase it, But no, they didn't increase it. What they did is added a weight. Now this weight was manipulated in a way that it was always positive. For negative terms was also positive. The duration was also within one, was like till one, and it didn't exist after a certain number of points. So it was only existing for points that were greater than, else it was 0. So they tried weighting it, and how they weighted is like give lesser weight to the autocorrelation at higher lags. Now, why at higher lags a lesser weight? Just to minimize the fluctuation that we are having there, the variability that we are having there. So in this way, they did. It's like try doing this particular approach, and this approach was, again, we also term it as Blackman-Tukey spectral estimator, but we also called it as weighted covariance estimator. Why covariance? Because we see that the autocorrelation function has a weighted function, and then if you recall what we had initially, take the Fourier transform and then split it up into two terms, it's essentially the covariance. So the new estimator over here, it again won't, it's like does not guarantee that what we are getting is non-negative spectral estimate. So then how we should make it, or how it generates this negative estimate. So let's see that. So we had the same thing, the Fourier transform of the weighted function as well as the autocorrelation function. Then we take the convolution of it. So we saw that okay, both of them are same, of the estimated periodogram as well as of our autocorrelation function. So then now here this factor, this particular equation, this can be negative since it's again delayed and shifted. So if it's delayed and shifted, it can be negative enough to cause a negative estimate. So in order to ensure that it's a positive one, the lag window should have a non-negative Fourier transform, or equivalently, our function or the weight would be positive. So again, there were other people, that is Bartlett and Parsons. So Bartlett is the one who gave this our triangular window approach to satisfy this condition. So they again saw that this unbiased autocorrelator estimate might also give something as negative estimate. So that was not good enough. So they again changed the weight function, and then which boils down to the original periodogram estimator. So they tried a series of techniques, but then essentially came down to point one. But then what they saw is that the mean value of this Bachmann-Tukey spectral estimator is smeared version of our true PSD. So now the variance is also similarly the square of the weighted function as well as a power spectral density, take it out. Now here divided by the average function that we have by the total number of points. So what we see over here, it's essentially, it's like how we smooth it over any frequency, it's equal to the bandwidth of the main lobe. So what bandwidth was, I hope you all remember, the negative 3 will be, okay. So it's like the difference in between these 2 points. So this is nothing but the bandwidth of a particular signal. And it's like say at two different frequencies, say f1 and say f2 over here. So that is equal to the bandwidth of the main lobe of the spectral window. So so the frequencies which are not near to 0, so they say that okay, if it's say plus starting from positive 0.5 or negative 0.5, the variance was given by this. So again, they are taking the window as very symmetric window and it is centered at 0, but they are saying that it's not starting from there, and they are not defining for those particular points of function. So then first point to keep in mind over here is that for this kind of estimator, the bandwidth is equal of the main lobe is equal to over the entire frequency. The PSD of entire frequency, the bandwidth is only about the main lobe of the spectral window. So then the variance is given by this. So again, there's always a trade-off in between the bias and variances. Like how do you see and define that if the bias and variance, both of them should be lesser and lesser. So they say it's like someone did some experiments and saw that okay, this particular kind of term would be more appropriate and to tune of that m. If m is 1/5 of this n, they saw that okay, both the values could be took down to a minimum value, so that if n tends to infinity, it won't be an unbiased estimate. So that was still the Blackman's Tukey spectral estimator. Let me know if you have any doubts, because I didn't stop at particular point. I thought okay, it's going. If, do you have any questions or doubts till this point?
No, ma'am.
No, okay. So we'll go towards the last one. That's the Daniel spectral estimator. So in the Daniel spectral estimator, what he did is that he took the Fourier transform and then he applied the moving average filter in the frequency domain. So people are not yet done with the averaging part. They are very obsessed with averaging. So what now he proposed is that instead of giving a weight, instead of giving any lags to it, he did unweighted averaging. He didn't add anything, and that's a function for it, how he defined the spectral periodogram for himself. And he said that okay, it's a smooth periodogram because essentially we are having more number of points in there. But if you see the terms and the limits, it's more of similar to how we did initially. But a nicer and it's like a smart way to do over here was that he applied the averaging in the frequency domain. So now you have an idea that how a particular estimate in the frequency is varying at from time points or from a particular instant to instant. So there you can manipulate it accordingly. So he said that okay, the FFT is performed in order to compute it, and this is how the duration of the frequency function was. So there were different kinds of functions, like measures from this PSD, the moments of PSD. So first was the total energy of the signal. So you know this basic function or definition of the total energy is like take the square and then magnitude of it. So then after a point like 1 by 2 pi of this particular point, okay. Okay, Ayush, you asked a question, right? You might want to see this function, this definition. I guess, should get an idea about it then. Okay, so then if it's in the frequency domain, if you split it up into f, it would be essentially from 0 to 1. So the first order moment, and so there are different moments over here. There's first order moment here, there's second order moment here. Just keep in mind what this moments are is like if expectation is e of x, first order moment would be x e of x, second order moment would be x square of e of x. So if it's first order moment, again in the frequency domain, this is a power spectral density. So if it's s of s is like the spectral density of the function with itself times of f. And here again essentially the terms which we need to average it around, and it's like if it's in continuous domain like this, if it's discretely defined, if it's like this. So then if it's a median frequency, so you know what median frequency is like. So the centermost point, if an odd number of points are centermost even, so you took the average of both of them. Sorry, like that. So the median frequency over here essentially defines the shape of the distribution. So this is how it's being given. And then if it's a variance, it's again x square times of s of x. So here it, if it's in the spectral domain, it will tell you about the spread with respect to the mean energy. So don't worry, I don't think so things like this would be asked or the formulas like this would be asked. It is just that you should know the significance of it. And if it's just given that okay, write the formula for variance of frequency, you know that okay, it's a second order moment, it's second order moment in the frequency domain. So you should be able to definitely write this part, and if not the constants in front of it. So always remember, if we need to average everything, so the division over here is by the expectation, is nothing but by the average of the signal. Instead of dividing by the total number of points, now in the frequency domain they average it by the expectation of the signal. That's it. So there are other terms here which tell us about the shape of the function. So one just is the skewness. So skewness is defined by this as like third order moment and then 3 by 2 power of it. So then what skewness tells us is that how much skewed your data is like. So if you have a Gaussian distribution, it's normally it's like symmetric across the y-axis. So about the origin. So but then if you have a data that's skewed towards the righter segment, so then if you see if it's skewer, more skewed data, so then there are different kinds of technique for it. So then essentially you need to first you need to estimate if the data is skewed or not. So this is how from the frequency domain you can estimate it. Again, how much skewed the data is, you can tell it from the kurtosis. What kurtosis is nothing but it tells us about the tail of the distribution or the function, is like how long the tail is. If it's more sharper enough, more wider enough, this kurtosis tell you about that part. So there's another factor called the spectral power ratio. Spectral power ratio is nothing but the division of the powers at two different bands of the frequencies. Say it's like within f3 to f4 by f1 to f2. So given if you have a signal which is from f1, f2, f3, f4, you take the last one by the initial one and just divide it up. So that's a spectral power ratio. Okay, so there are different applications for the same as like in PCG or in EEG, you apply the spectral power ratio kind of techniques. But then again, now we saw from previous that in physiological signals, now we have the exact bands where the signal is lying, or which kind of activity a particular function is behaving there. So you might want to do or apply the statistics or this kind of measures in that particular band. So you might get some physical significance from there about the signal or about the interest. So that was all about week 7. Do you guys any quick questions or doubts? You can ask me, or we'll go into the assignments. That previous year questions, 10 questions as usual.
Ma'am, I have a doubt still in that question.
Yeah, yes. So,
So
you,
limit will be from 0 to pi for the positive. Because ma'am, in this integration, ma'am, limit is given 0 to 2 pi.
see, don't mix some things, but I told you this because it's in angular frequency. This is in the frequency. Uh, to y you were relating over here was in f, I guess. The negative 1 by 2 to 1 by 2 over here, it was in f. Now if it had to be in angular frequency, the terms would vary. So that's the only hint that I can give you for now.
So ma'am, limit will be from 0 to pi only.
Up to you. What do you think? It's like, see how the periodogram is, what defines a periodogram, and then how a periodogram should be. So accordingly, what weights you choose for that, and what should be the range of those weights. That's it. Okay. If no further questions, then we'll go into the assignment then. So the periodogram can be a consistent estimator of the PSD if here n is the number of samples. So did we have anything about n over there, that if n is say 1000 or 1 or 0?
Option C, ma'am.
Which option?
C.
C. Why C? It's like we saw that if it's a consistent estimator, we saw that the bias of it and the variance of it or a mean of it was some estimator over there, but we didn't see that there was any constant of this on the number of samples. So it's actually none, because if it tends to infinity, it can be biased or unbiased. So we don't, if you just take a single sample, it won't be. It's like you can't actually determine the PSD of it. I hope you got the difference. Okay. So the output of a periodogram at a given frequency, if not, represents what? The power, magnitude, phase, or nothing.
Is it A?
Ma'am, I think option A.
Yeah. So it gives us about the power of the function at a particular frequency. Essentially, the power spectral density. So a periodogram of a given signal x of n is defined as formula. Now you know how the periodogram is defined, what it is, Fourier transform, limiting case, average it.
Is it A and B?
It ideally should be A and B, but then here, if you see the limits here and here, it's like it is again dependent on x. So we should have a term over here and then averaging estimate. So it's not there. So it's only A for now. That's it.
Oh.
Next, which of the following statements are true for your periodogram? Given n is the number of samples, that it's a constant independent of n, dependent on
A
n,
and C.
is a reliable estimator as big as me. Yeah, an.
A
Is
and
it?
D.
Oh, sorry, ma'am,
Which?
unreliable estimator. Yes, ma'am, A and D.
Okay. Yeah. Okay. Blackman Tukey suggested using the window for to eliminate, to reduce, to give more importance to accurate estimates. Okay.
All of the above.
Yeah. Okay. The spectral power ratio of a I guess it's just we just need to see the limits and the magnitude. If it's squared, cubic, or
Is it
closed.
C?
Yeah. Yes. Okay. Which of the following is true for filtering windows? The wider the main lobe, greater the spectral smoothing. Wider the main lobe, slower the smoothing, or loss of the spectral resolution is more, or loss of spectral resolution is less. Probably two options would be correct over here, but I'm not so sure. Need to look.
BC.
Wider it, low spectral, and loss of this is more. AC. So wider the main lobe, greater. If it's wider, more the spectral smoothing would be there, right? The function would be more smoother, and this was right that the spectral resolution would be lesser because we measure it using the main lobe. That's it. Okay. So which of the following is true concerning the main lobe for the same number of samples? So for a filter function, I hope this is visible, the slide. So if for Hamming-Hanning it's same. I don't know if we saw, but I guess in the lecture slides, it's like for the video lectures, it was there for Hamming and Hanning a Fourier transform function for the same. So if it's the same, if it's greater, lesser, or this.
Is it A?
Yeah, it's A. But if I add rectangular function in there, what will happen?
Rectangular will be the highest.
Yes. Okay. So these are something that they added last time. I don't know. It doesn't even relate to the slides, but okay. Normal hat sounds contain high frequency components, low frequency components, both of those components. So
C?
essentially, no, it's high frequency components because sorry, it's B. Low frequency components because respiration we have high frequency components. So because of the activities that we see and the sounds, heart sounds is like S1 and S2, their frequency is not essentially above 1 hertz or 1. It's like all everything less than 50 hertz. So,
But if we talk about the noises, then
but
in
it's
some
only
of
about
the
the heart
previous,
sounds, not with the noise.
but if we take the practical example, so noise is a
Yeah,
like
it's a
high
high frequency
frequency
component.
component, na?
Yes,
That's why I use high pass filter to detach it.
eliminate. Yes. If you see in that way, it would be both high and low frequency. Okay, so this is, you can just open up your calculators and do this. Like for a normal human heart, the RR interval is, so normally we have our heartbeat as 72 beats per minute. So what can be the RR interval rate? Guys, 72 beats per minute.
0.833 seconds.
Yeah,
0.833.
yes. So 60 by 72, we have 0.833 seconds. That's it. Done for today. Thank you. If you have any questions, you can stay back and ask me. If not, thanks for joining.
I still doubt in that limit question.
So, okay, wait. I will share the screen again. I'll give you a brief idea about it. This one, right? Huh. So, to obtain a smooth spectrum, okay, if not me, I guess some of your bias, like the people who have joined over here, can help you. So, what do you guys think? The parallelogram S of omega, when it's convolved with this filter in the frequency domain, which of the conditions should be satisfied with this filter or this weighted filter? So, we all know that now it should be positive. We don't even know that, okay, if it's positive or not, but to get a parallelogram and it's smoother parallelogram, we want to ensure that it's a positive estimate. So, okay, this hint is solved. So, what would be there if, how do we define the weights of this as like the frequency domain, the range of it? Take it as an assignment or question. Try it.
Ma'am, according to me, it may be A or B.
A or B. Probably it can be, or it can be both. So now you know that it's not negative, right? So
Yes, ma'am.
yeah, you have to estimate from this two only. So if it's negative pi to positive pi, you'll have to see that what happens. I guess there's something for the formulas. We saw that it was both sided, and in the end we took from perhaps this slide only. So you can just have a cross check from what do others think? It's like Sri Naresh, Harsh, Yash, Meg. You're also doing this assignment, right?
Ma'am, I think that the limit 0 to 2 pi may be because they must have taken the property, that integration property minus a to a, and if a is a and if x of n is a even function, then we can write 0 to 2a, or if a odd function.
Mm-hmm. Someone was saying.
Ma'am, there is a, please open the assignment part that we are doing, assignment R.
Oh.
In that there is a question that uh, for the, there is a question related to spectral power something. Wait a minute.
This.
Ma'am, please slowly, little slowly.
Oh, sorry.
Wait a minute. That one only, I think fifth one. Yeah.
This one.
Yes, ma'am. So here it is given the wider the main lobe, the greater is the spectral smoothing. I think this is the answer, 7th A.
Ha.
Okay. So by taking this reference, now open that question. Okay. So if we want the smooth spectrum, then Bradley means the three types that we have seen. There are mainly four types. So rectangular, we can, no man, that is not knowing. Sorry.
You're actually now going through each and every keyword. No, but it's fine.
If we apply a basic logic, I don't know if it's correct, but if I go according to the angular distance, so
Yeah.
0 to 2 pi, that distance, it would be same as option B, minus pi to pi. So distance wise, can we look at it?
You can, but it's just a matter that okay, you need to. Then it's like I'm not so sure how. Probably both of the options would be correct, but it can be a way to look at it. Can also be a way if you are representing the frequency domain as f or omega. Can also be a way how I you said before that. It can be both of them, so it can be a way.
Ma'am, in your opinion, according to your opinion, ma'am, which option might be the most accurate one?
I don't have an opinion at this point of time. Okay. You have any further doubts? All of the questions were fine?
Yes, ma'am.
I guess you were fine, huh?
Actually,
Ma'am?
this assignment was ma'am, most of the questions were not from the video. Like the last question, it was not given, but eventually I
Ma'am?
found on YouTube.
This one?
Yes, ma'am. Ma'am, in ma'am, in none it was given.
Yeah, yes. So it's like input signals are rectangular waves of
Ma'am, can
different
you
length.
please go to the question again?
Okay. This.
Okay, ma'am. Ma'am, we have seen that in every of the window, if we see by the diagram, that is, if we go through the lectures, then every window is symmetric. Every window is symmetric. And if we see, so every window, I think weight's also greater than equals to 0. Like if, and mainly there are three observations that if in n equals to 0, if we do the n equals to 0, then we get the maximum energy, like peak. So by these keen observations, I think the option B is most appropriate.
You can go ahead then. So it's true, it should be symmetric, it should be positive. But then the symmetric part is not with respect to these two limits, it's some other limit. But yeah, it also follows with this limit too. So,
Minus n to n something, no?
huh?
Minus n to n something, na? If we see the
Yeah.
data.
Yeah, yes.
Okay, let's see.
Right, it's fine. Even if you lose 1 point, won't be a case. It's like how's your scoring till now? From first assignment to last is like this 6th assignment. How about grades? Were it fine?
I'm in 5 assignment. I got 100 and in 190.
Yeah, that's fine. It should do. It's nice. So for this lecture also, right? You guys are already doing your best. Right. Also, your fundamentals are clear, so should not be a problem. Now I won't say answer over here. If you have any doubts, you let me know.
Thank you, ma'am.
Thank you.
Thank you.
Thank you.
Thank you.
Thank you. Thanks for joining.